Okay, let's continue with the tension. Suppose we have this mass, the wall, and let's say it's massive. We have a massive string of length L. Let's assume that its mass density is rho. What do I mean by mass density? Is the rho is equal to mass divided by length. It is the mass per unit length. So that's also why sometimes it's called linear mass density. What is the tension? What is the tension at any point on the string?
Weight.
Equal to weight. Weight of what? Weight of the string. Okay, so there is one answer. Tension is equal to weight, which is equal to mg. By the way, what is m? There is no such parameter in the question. There is no such parameter in the question. So it's equal to rho Lg. The length. So let's solve it. You see, I know the answer. I don't want to know the answer. I just want to know how you obtain an answer. Now, let's discuss it together. At any point on the string, that's what I want to find. I just give you this point, let's say, what is the tension at that point? What is the tension at this point? Is it the same everywhere? Or does it change from position to position? How does it change from position to position? How do we calculate that change in the position as a function of position, if it depends on the position?
Uzunluklarını tam uzunluğu o noktadaki uzunluğa oranlayıp çarpsak. Yani
Well, let's solve it step by step. The first thing is, how do you plan to specify the point, the position of that point? So you kind of have to write an expression which first should specify the position of the point. There are many ways you can do it, but you first have to tell me or whoever is reading your solution how you do that. Okay, which point? Which one?
the point where it meets the...
Okay, so this is the reference point. And then we choose a direction. Let's say this is the x direction. So if you take any point over here, this will be, let's say, the h. Let's call it h. So if you tell me this distance h, then I know the position of the object. So the question is, what is the tension? Then, oh, this is wrong, by the way. When r is equal to h, at this point, what is the tension? Now we can apply Newton's laws. Let's just consider this part. Of the string. Now let's first draw what we call the free body diagram. Now this part of the string, since there are no forces that would cause it to change its shape or cause deformations, I can still apply Newton's laws. Although it's not a point object, I can apply Newton's laws because it's not changing its orientation, it's not changing its shape. So I can still apply Newton's law. Now, let's just imagine this point is my mass. This whole string, I can just represent it by this point. It just behaves like a point object. What are the forces acting on it? There will be gravity. Gravity is a force. There will be the weight. There will also be the force due to the tension at that point. And let us just denote it by this vector t. And these are the only forces acting on my object. This is what we call a free body diagram. Now, the important thing about the free body diagram is that it only shows the mass that we are studying, we are looking at. It doesn't show anything else. It only shows the forces acting on that mass. And it doesn't, there's no components, etc. Only the forces and the mass itself. That's the only thing. That's why we call it free. It's free from all the other obstacles. Now, the tension force, how can we write it as a vector? The force created by the tension. It is T, it will be pointing in the minus x-hat direction. The weight, the force due to the weight, is mass times m times g. It is in the x direction. So the net force acting on my mass, total, will be just the sum. It is mg minus t. The net force is, again, the sum of these two vectors. It's not the difference of these two vectors. It is the sum of the vectors. But the sum of these vectors is mg minus t in the x direction. And this should be 0. By the way, m, let's just denote it by mh. Because it's not the total mass of the string. It is the mass below this distance h. It is the mass of this part. So the tension will be mh times g. Now, the next thing we have to determine, what is mh? The length of this part is just L minus h. And we are given that the mass per unit length is rho. So we don't have unit length. The length that we are studying is L minus h. So mh is equal to rho times L minus h. And so the tension at the point h, at the point specified by this number h, is equal to rho g L minus h. Now, sometimes close to the midterms, the students start asking, can you give us some sample solutions to how we should solve the questions in the exam? Well, this is the sample solution. This is what I expect from you in the exam. You should, well, I even expect more than this one. I want you to first explain me, write to me how you are planning to solve the question first. Here I'm just taking it out, I'm just telling you my strategy. I'm expecting you to write your strategy in your answer. First, write your strategy, choose reference points, coordinate axes, write your vectors in terms of the components using the coordinate axes that you have chosen, and then you just calculate the total force, use Newton's second law, etc. None of the steps that we had done over here is unnecessary. All of them you should do. Okay, any questions on this one? Okay, let's look at this concept of weight a bit in more detail. We said that, okay, the weight is m times g, but there's a bit more than just m times g to that. Let's assume that you take an elevator. This is the elevator. And the weight, basically, you measure by a scale. Here is a scale to measure your weight. You stand on the scale. Let's say you're in the 0th floor and you click and you want to go to the 2nd floor. So at the moment that you click, the doors close and the elevator starts to move. In which direction is the elevator moving? Accelerating. What is the direction of acceleration? You are in the 0th floor, you are moving in the you are going to move in the 2nd floor. The acceleration of your acceleration is downward, upward, up or down? Well, there is only acceleration. There is nothing called the net acceleration. Is it upward minus g or something else? It's up. Well, you see, initially you are at rest. When the elevator starts moving, your velocity is pointing upward. So the change in your velocity vectors is upward direction. So your initial acceleration is pointing upward. What are the forces acting on you? Okay, so this is you. Let's say your mass is m. This is the free body diagram of you. Now, what are the forces acting on you? Somebody else? Beyond the usual suspects? What are the forces? What are the forces? I'm not asking for the acceleration. What are the forces acting on you?
Downward g-force.
Okay, downward weight. Okay, you have this weight. The scale is pushing us up. We cannot go through the scale, so the scale should exert some force on us. Now, that force, what we usually call the normal force. Okay, this is the push of the scale. Does the elevator exert you a force? It doesn't exert you a force. If it's not directly exerting a force, it's not exerting a force. There is no force due to the elevator. You are not even touching the elevator. There is no contact with you. There is no force between you and the elevator. The elevator exerts a force on the scale, and the scale exerts a force on you. So these are the only forces we have. Again, let's choose some coordinate axis. Let's just choose this one as our z-axis. It's just arbitrary. Now, since we will be dealing with accelerations in inertial reference frames, we don't really have to specify a reference point. Because as long as you are in an inertial reference frame, the acceleration is always the same. The force sense is always the same. So if you want, you can still specify a reference point, but for the time being, we will not need it. So what is the normal force? We don't know its magnitude, but it's in the z direction. That is something we know. The weight, we know that its magnitude is m times g, and it's in the minus z direction. So the total force acting on you is the normal force plus your weight, which is n minus mg of z. Again, I repeat, to calculate the net force, I always sum the forces independent of the direction of the forces. This minus sign is not because I'm subtracting these two forces, this minus sign is because of the direction of the weight, which I already taken into account over here. And well, we are also told that it has a direction in the upward direction, and this is the acceleration vector. So what should be this total force? Well, the mass m is also accelerating with the elevator, unless you're just you just crash on the ground or you start flying, you will be accelerating with the elevator. So if the elevator is accelerating with an acceleration a, that is also your acceleration. So this should be equal to m times a in the z direction. Your acceleration vector is magnitude in the positive z direction. So the normal force minus mg is equal to m times a, or the normal force is m times a plus g.
Just a while back you told us that since the force isn't directly in contact with us, then the elevator doesn't exert a force on us.
True.
So how can you say that since the elevator is accelerating upward, we're accelerating upward, when there's no force from the elevator on us?
You see, the elevator exerts a force on the scale. So the scale is accelerating with the acceleration a. The scale is exerting a force on us because we cannot just go through the scale. So we have to be accelerating with the same acceleration as the scale itself, which is accelerating with the same acceleration as the elevator. The only force over here is acting on us is the force that the scale exerts on us. So what the scale reads as your weight is nothing but the normal force that it exerts. Or you can say that, okay, this is the force that the scale exerts on us. So we are exerting exactly the same force on the scale, just in opposite direction. And that is what the scale reads. So the scale will tell us that our weight is m times a plus g. Well, it's a plus g. We will appear heavier. You see, our mass is the same. Our mass is independent of the circumstances we are in. Whether we are in an elevator accelerating upward or whether we are on moon, our mass is the same. It's independent of external properties. It's a characteristic of the object itself. It doesn't depend on the circumstances. But your weight depends on the circumstances. For example, in this example, your weight, you are heavier because you are in an accelerating elevator. Or if you go to the moon, you will be lighter because we will see that the g on the surface of the moon is much smaller than the g on the surface of the earth. So your weight changes depending on where you are, but your mass does not. Now, what if the elevator is accelerating downward?
You just take minus sign of A.
Well, you see, we don't have to do anything, in fact. This is the acceleration. If A is positive, it just means that the elevator is accelerating upward. If A is negative, the elevator is accelerating downward. So you can just imagine that you reach the second floor and the elevator is stopping. You are moving upward, but your acceleration is downward. So in that case, A is just negative. This result will still be true, but in this case, A will be negative. That will be the only change. Since if you are accelerating downward, A is negative, you will appear lighter than when the elevator is going up. Well, this is something you should have been experiencing. If you take the elevator, if you didn't take the elevator up to now, just take it now when you go to the department, press the button. When the elevator starts to move upward, you feel as if you are pushed downward. That is basically your weight appears larger. Or when you reach the second floor, the elevator is stopping, you just feel as if you are being pushed upward. That is basically you are not at that during when the acceleration is downward, you are lighter. Now, another thing that you should pay attention to, this normal force. Okay, quite often the students write the tension is equal to mg or the normal force is equal to mg. Normal force is not equal to mg. Normal force is as big as it should be to prevent you to move through objects. If you cannot move through objects, that means that object is exerting a force on you. And the magnitude of that force is big enough to prevent you to go through. In this case, the scale is exerting a force on you, this normal force. If there is no acceleration, the normal force that the scale should exert to prevent you to move through the scale is just mg. If there is an acceleration, then it is given by this force. The normal force can have different values depending on different circumstances. It's not equal to the weight all the time.
So how does the mass absorb force exactly?
Mass doesn't absorb a force.
Just a minute ago you said that the surface how
Exerts a force.
exerts.
Yeah. No, you see, there is no force pushing us downward. If you are taking the elevator, you feel as if there is a force pushing you downward. Because, hold on. You are in the elevator. You press in the 0th floor, you press the button to go to the 2nd floor. The moment the elevator starts to move upward, what is actually happening is that the elevator is pushing you up. So you feel a lot stronger force at your feet. While you, as human beings, we feel a larger force on our feet if we are pushed down. So that is why we feel as if we are being pushed down. But that doesn't mean there is a larger force acting on us in the downward direction. It's a non-inertial reference. Our reference frame, the reference frame fixed on us, is a non-inertial reference frame. So we cannot really use the Newton's laws in that reference frame. If we want to use the Newton's laws, you have to first go to an inertial reference frame, which is outside, let's say fixed on Earth. In that reference frame, you are accelerating upward, so there is the force exerted on you is large, should be larger than your weight. The normal force is larger than your weight if you are going upward.
Can we feel this force? Not force, but
You feel as if you are being pushed downward. The weight, well, it is pointing in the positive x direction.
Depending on the axis?
Sure. Now, you see, weight, the force created by the weight is always positive. You are either weight like 700 newtons, 800 newtons, 600 newtons. That's the weight is the magnitude of the gravitational force that you are feeling. The gravitational force that you are feeling, that I use this symbol to show, the omega vector, its components, of course, depends on which way you choose your axis. If you change your axis, its components will be different. Let's do another example. What is the acceleration vector of this object? This is theta, no friction.
I have a question in the last place. When the impulse have lost, while two bodies interact, the forces on the bodies and the magnitude are the same and opposite reaction.
True.
In here, the scale exact force on the man in a normal force, but opposite reaction in force.
Now you see here, okay, this is the force that the scale exerts on the man. And Newton's third law just tells me that the force that the man exerts on the scale has the same magnitude, m times a plus g. It's just pointing in the minus z direction, the reaction force. You see, the mg, if we take the scale in this case, let's just study the scale. What is the free body diagram of the scale? What are the forces acting on the scale? The weight of the scale. No. The weight of the person does not act on the scale. There is a force due to the elevator. Let's call this N prime. And there is a force exerted by the man. Let's call it N double prime. Now the magnitude of this N double prime is equal to N. The weight of the man only acts on the man. It doesn't act on the scale. The weight of the man creates this N double prime. If the man doesn't have any weight, that's only possible if it doesn't have any mass m, then there won't be any N double prime. The weight of an object is nothing but the gravitational force acting on that object. It doesn't act on any other objects. Of course, the weight will cause other forces to be created in the system, like these normal forces, action-reaction pairs, etc. But what acts on the scale is not the weight. It is this normal forces.
Acceleration is the 5 and your g minus or minus 9.
You see, g is always and always 9.8 meters per second squared. Your acceleration, let's say your weight, is minus mg because we are choosing the z-axis to be upward. G just stands for 9.8 meters per second squared. G is never minus 9.8 meters per second squared. It's always and always 9.8 meters per second squared. Rather than writing 9.8 meters per second squared all the time in our expression, we just put G. Let us assume that you stand on this table and then you just jump down. What is the acceleration of Earth? So this is Earth. You are standing over here and you just jump down. After you jump, what is the magnitude of the acceleration of Earth?
According to your G, vector is minus G.
Order of magnitude. I don't want the exact number. The answer is not G.
Related to what?
To any inertial reference frame.
Zero.
0, G. Okay, the answer is 0, G.
9.8 meters over second squared.
That's G. your weight over the mass of the Earth, which is, well, let's see, your weight is something like 800 newtons. Mass of the Earth is something like 10 to the power 24 kilograms. This is something like 10 to the power minus 21 meters per second squared. Or we can also say that this is 10 to the power minus 22 G. Absolute G. G is a positive number. G is 9.8 meters per second squared. Its absolute value is 9.8 meters per second squared. Any other answers?
We say, well, what I noticed is that we don't have a coordinate plane, but we can give the direction of the acceleration.
Well, I'm looking at the magnitude of the acceleration. And the acceleration is independent of the inertial reference frame you choose. Okay, the third one. Your answer was?
0.
Okay, so it's not 0. Okay. Forget about the sun. I mean, let's just assume that the Earth is isolated in empty space, there's no sun, etc. And you are so depressed that you want to, there's no sunlight, you are depressed, you want to commit suicide, and you just jump on the top, from the top of the building. Probably the last thing you will care about will be the acceleration of the Earth, but we might be interested in that. So what will be the acceleration of the Earth? Okay, so what will be the force that you feel? You won't feel any force. You are close to Earth. No, you will still, the net, you see, you are accelerating, right? So there will be a force acting on you. There should be a force according to Newton. So what is that force? Well, basically your weight, m times g. That is the force that will be exerted on you by Earth. That is Newton's second law. Since you are accelerating by 9.8 meters per second squared, there is a force, there should be a force acting on you, which is your mass times this one, your acceleration. The Earth is exerting this force. But Newton's third law tells us that you are also exerting exactly the same amount of force on Earth. So Earth is exerting like 800 newtons on you. You are exerting 800 newtons on Earth. Well, that is the force acting on Earth, but the problem is the mass of Earth is huge compared to you. It's like 10 to the power 24 kilograms. This is the mass. It's something like 6 times 10 to the power 24 kilograms, but 6 doesn't really make any significant difference. So this is the force that is exerted by you on Earth. This is the mass of Earth. So the acceleration of Earth is given by 10 to the power minus 21 meters per second squared. So how far does Earth move in this time? How much? An order of magnitude estimate. Now this is what we call an order of magnitude estimate. I don't care about this 8 or whether this is 9.8 or 10. Of course, if I put the exact numbers, the number will be 10 to the power minus 20 or 10 to the power minus 22 or something in between, but who cares? I mean, the message will be clear. It's small. That's the important thing that we are looking at. Whether it is as small as 10 to the power minus 20 or 10 to the power minus 22, it doesn't make any difference. It's small. So how far does it move? How long does it take for you to fall from the top of an apartment building?
Not more than 5 seconds.
Well, the height, let's say, is 100 meters typically. Now, even that is quite high. 100 meters will be 1.2 times 10 meters per second squared times t squared. So t squared will be 20 seconds squared. So the time will be something like 4 seconds. I don't care whether it's 4 or 5. The displacement of Earth will be something like 1/2 times its acceleration. But I even don't care about this 1/2. 10 to the power minus 21 meters per second squared times, well, it's 20 10 to the 1 second squared. So this is something around 10 to the power minus 20 meters. So this is how much Earth will be displaced if you jump down. Do you remember the size of an atom? Size of an atom? Radius of an atom is typically 10 to the power minus 10 meters. So the Earth doesn't even move one atom. So that's why you don't feel the motion of the Earth. Well, the same thing applies if you are, let's say, if you are swimming in the sea, you just push a huge ship. The ship will not move. I mean, the forces that you exert on the ship and the force that the ship exerts on you, they will still be equal in magnitude. But since the mass of the ship is huge compared to you, although not as huge, still the acceleration of the ship will be 0. And during the time that you can exert a force on the ship will not move at all. I mean, the displacement of the ship will be less than, again, the size of one atom. So you will not be able to observe it. Although you are exerting exactly the same force, your acceleration will still be different.
So what happens when does it move at all? Even less than an atom's length, but does it still move at all, or does nothing happen at all?
It does move.
It does move, right?
Yeah, sure. It should move. I mean, what happens if 5 billion Chinese jump at the same time? Well, that's always the question asked. Nothing. Well, soon it will be Indians. They have a larger population. So, any questions on these ones? So what is 1 billion, 10 to the power? 10 to the power, let's say 9. 10 to the power 9, just multiply this by 10 to the power 9. The acceleration will be 10 to the power minus 12. Well, the motion of the Earth will be like the size of one atom. Smaller than that one. Nothing. Okay, now let's go back to this mass of an inclined plane. Now there was this question, how do we know that the normal force is vertical to the surface? Now we had already discussed the normal force over here. We said, okay, the normal force has to be in this direction. Now here there's no friction. We are on an inclined plane, but we will still say that the normal force is perpendicular to the surface. This is the normal force. So why not at some different angle? Yeah, it's basically its definition. There is a force that this surface exerts on our mass m. That force can have a component perpendicular to the surface and another component horizontal to the surface. The horizontal component is what we call the friction force. Since there is no friction, we are told that there is no friction force. The only force that the surface exerts on the mass is perpendicular to the direction to its surface. So this is the normal force. Now let's draw the free body diagram first. I mean, whenever you are discussing such problems on the applications of Newton's laws, you always start by drawing the free body diagram. Here we have a single mass. We are assuming that the inclined plane is fixed. So this is our mass. So what are the forces acting on this mass?
Weight down.
Okay, the weight. Normal force. Are there any other forces acting on it? No, nothing else. These are the only forces acting on my mass. So we should choose some coordinate axis. So who wants to choose one of the axes horizontal to the plane? How many hands? 1, 2, 3, 4, 5. Okay. Who wants to choose the vertical axis as one of your axes? Okay, you can choose your axis in whichever direction you like. Vertical direction is nice because the gravity is in that direction. Horizontal direction is nice. You can choose one of the axes to be this horizontal to the inclined plane because the motion is along that direction. But you cannot choose both of them. So we had the larger votes for this one. Let's say this is our x-axis, this is our y-axis. Now if you choose these coordinates, the normal force is it right? It is. We don't know its magnitude, but we know that it's in the y direction. Now the tricky part will be what is the weight in terms of its components using these axes. And that we will discuss in the last hour. Now before you go for a break, any questions? Not on this example, we will continue this in the next hour, but on any other thing that we had discussed. Now, weight is defined as the gravitational force acting on you. Yeah, I mean, the perpendicular component we call the normal force, the horizontal component we call friction. Well, the weight is the magnitude of the gravitational force, to be more precise. Well, gravitational force is the force. Gravity is like the concept. I mean, is there a difference between physics and physics lecture? Yeah, I mean, physics is more general. It's not necessarily a lecture. Gravity, you have the gravitational force acting on one mass. You have the why is there gravity to start with, etc. Gravity is the concept itself. Okay, see you.